Hello guys, in this section we want to talk about a topic dynamic programming. Dynamic programming is a useful mathematical technique for making a sequence of interrelated decisions. It provides a systematic procedure for determining the optimal combination of decisions. In contrast to linear programming, here, we don't have a standard mathematical formulation of the dynamic programming problem. Rather, dynamic programming is a general type of approach to problem solving, and the particular equations used must be developed to fit each situation. So, to this end, in this chapter, through many different examples and the different forms that may happen in dynamic programming, we try to review this concept and learn the structure of this example. What we do in this chapter is starting the concept of dynamic programming with an introduction. Then, through a prototype example, we review the different concepts of dynamic programming and the objectives and the process of solving the problem. The next step is explaining a little bit the characteristics of dynamic programming problem that we'll see there are 8, and after solving a prototype example we are able to detect all these characteristics. Following up this section, we go towards reviewing the concept of deterministic dynamic problems and probabilistic dynamic programming problems. And finally, we conclude this section with a conclusion of this chapter. As I told you before, dynamic programming is a mathematical technique to make a sequence of interrelated decisions with the end of finding the best and optimal solution and decision among many different alternatives. Okay, so this is our end to find this decision based on what we want to do. For example, maximum the output or minimize the cost or whatever. So as we reviewed, in contrast with linear programming, there is no standard mathematical formulation to solve the dynamic problem. But for sure, there is a general approach to problem solving for dynamic problem and use of a specific equation for each case based on this general problem solving. But the approach always is the same based on the different examples. This becomes different. So we must acquire a certain level of criteria to understand the general structure of dynamic programming and know how to recognize them. To this end, we should start with a prototype example to be familiar more with the concept of dynamic programming and moving forward to the next steps. In this slide, let's talk about a prototype example and a little bit describe what it exactly says and what is the objective of that. This famous example is specifically prepared for the concept of dynamic programming, the stagecoach problem. It concerns a mythical fortune seeker in Missouri, United States, who decided to go west to join the gold rush in California during the mid-19th century. So what we have here is moving from east to west, okay? So the journey would require traveling by stagecoach through unsettled country where there was serious danger of attack by marauders. So what is the meaning of that? It means that based on the destinations and based on the stops of this fortune seeker in different cities, okay, and the different milestones in the way, there are many dangers, and we should think about them. Although his starting point and destination were fixed, he had considered choice as to which states to travel through en route. Okay, so we know he starts from Missouri and he finishes in California. But between these two parts, these east to west, there are different options, there are different ways, there are different roads that this fortune seeker can select. The possible routes that are exist for this fortune seeker, we can watch them in the next uh, slide. We can see them where each state is represented by a circular letter, and the direction of travel is always from left to right in the diagram. So guys, we should be clear with this, be careful to this concept that always, because we are moving from east to west, okay, always the direction of movement is from left to right, okay, so there is not a way coming back to other city and again moving to right, always from left to right. So as you see in the next slide, there are 4 stages where required to travel from the point of embarkation in state A, Missouri, okay, state A is Missouri, and state J, that is destination of this guy, that is California. So this fortune seeker was a prudent man who has quiet concern about his safety. After some thought, he came up with a rather clever way of determining the safest route. Life insurance policies were offered to stagecoach passengers. Okay, so based on the level of danger of each cities, the life insurance company offers a service of insurance to this stage to this fortune seeker. Obviously, the more dangerous the city, the policies and the life insurance more expensive. So the safer, the cheaper. Because the cost of policy for taking any given stagecoach run was based on a careful evaluation of the safety of that run, the safest route should be one with the cheapest total life insurance policy. What I told you. So the result and the uh, item that we are searching for is choosing the safest route by minimizing policy cost. So for sure, when we want to find the safest route, obviously it will be the cheapest cost for the fortune seeker, okay? Because as I told you, the safer, the cheapest. So let's review it in the next slide. So as you see here in this video, these are the nodes and the cities that this fortune seeker wants to move from Missouri, okay, to California. So this guy should decide about the different stages, okay, this stage, this stage and this stage to reach to this stage, to arrive to this stage. With what form? To minimize the costs. As you see here, these numbers that are located here are the costs of moving from state I, for example, to state J. So we name this cost as CIJ. For example, CAD is 3 levels, okay? 3 units of whatever, $3, okay? So one solution that is not related to dynamic programming is selecting from left to right the cheapest option. For example, among 2, 3, and 4, which one is the cheapest? 2. So we move toward B. From 7, 4, and 6, which one is the cheapest? 4. So we move toward F. From between 6 and 3, which one is cheaper one? 3. So we move toward I, and from I there is only one possibility toward J, that is 4. So if we add all these items, the total of this item, 2 plus 4, 6, 6 plus 3, 9, plus 4, 13. So this one could be an option, but by solving the dynamic programming, we'll see that there are cheaper solutions. So cheaper solution is one objective of this fortune seeker, and from the other side is safer. So for sure, if it's cheaper, it means it's safer. So in the next slides, by talking about the procedure, we'll find these different solutions that give us less expensive options. Another possible solution could be trial and error. Okay, in this example, because we are looking and the example is not very big and there are only 18 costs, by finding different routes and testing different routes, maybe we can find the minimum cost of this fortune seeker. But imagine there are more than 18. There is a very big example, okay, with different costs, okay, with different connections, and so it means that it's impossible to find the solution by trial and error. So as you see, dynamic programming is an appropriate solution for this game. So dynamic programming solution starts with a small portion of original problem, finds optimal solution for this small problem. As I told you guys, dynamic programming always is moving from left to right, okay, in this example. But to find the solution, we should start from the right-hand side and divide the game to smaller problems, okay? So, as you remember, I separated the different parts of this example as different stages, okay? And in each of these stages, we should find the optimal solution, okay? And add it to the next round, okay? To the next stage up to moving and arriving to node A, to the first node. So we should move and solve the example from right to left, like the decision tree that we had in the previous chapter. Okay, so always from right to left, and by separating and dividing the game and the example, to the smaller parts, make a decision about that and add it to the next one up to the very first node that here in this example is node A, that is misery. Okay, so the result is based on the objective that we are searching for. We are looking for what is the objective. For example, here is minimizing the cost of traveling from Missouri to California. For sure, the other example could be maximizing the profit, okay, from 2 points or from different examples that we'll see. So gradually enlarges the problems, find the current optimal solution from the preceding one. As I told you, we find the optimal solution, move left by adding that one, moving left to arriving to the very first point. And in the next slides, we'll see how we do this. When in the previous slide we were talking about the smaller problems in comparison with the original problem, we are talking about making a decision about these small problems. As you see, guys, all these elements are exactly those elements that we are watching here, and we are seeing them in this example that we had. Note that this one is very important. Always we don't have this graph like this. We'll see in our new examples that we have a list of a table, and based on the table we should make a decision that we'll talk about them later. But here at this moment, focus on this concept. This problem, this problem, this problem, and this problem is moving from node A to node J. As you see here, there are 3 ways from A to B to C to D with the cost of 2, 4, 3. There are 3 ways from B, C, and D to E, F, and G. Okay, as you see here, each of them have their costs, and there are 2 ways to from E, F, and G to H and I, and finally from H and I to J we have all the costs. So all this combination, all these elements are the make us able, for example, A, B, B, F, F, H, H, J, for example. Okay, this one can be a way. The other one says no, A, D, D, F, F, I, J. Okay, but which one? Dynamic programming, sorry, helps us to understand and select the results. How? I told you we start from the very last node, okay, and moving to the previous stage with the optimal solution of this one and adding it to this one. Okay, we find the optimal solution of this. Optimal solution of this one to this one give us the optimal solution of this stage, and finally this stage. When we are talking optimal solution, I repeat, based on the objective. Here we want to minimize the cost. So optimal solution for us is minimum. In the next slide, we'll talk about the solutions. Based on what I explained before to you, the example, this solution is a backward solution from right to left. We imagine we are at the stage when only there is one more step to complete this route. Okay, so when we are in the point H and I, so by moving a number by number of the stage, okay, we move toward left to solve the example and find the optimal solution and the route. To formulate the example, we should write and we should decide about some variables, okay? These variables are in general form xn. How many variables do we have here? There are four different decision variables: x1, x2, x3, and x4. That our x4 here is the node with name j. So we should make a decision as x1 between the variables b, c, and d. X2 is one of the E, F, G, and X3 is one of the H and I. And as I told you, X4 is our J here. So in this backward solution from node J to A, we should formulate always our problems, okay? Not only this problem, but also all of the dynamic problems. So to this end, we should write a function, for example, here, fn s and xn, is the total cost of the best overall policy for the remaining stages, okay? When we are talking about the best policy, it means that, for example, as you remember, among those nodes, for example, E, F, and G, we selected one of them that was the best one, okay? So all these best will be added to each other, okay, to find the total cost. Obviously, this best total cost in this case is the cheapest one, but as I repeated many times, it depends on the objective of the problem. So that S in this formula is the state that fortune seeker is in and ready to start stage N, okay, and selects xn as the immediate destination. As you remember in the previous slide, I defined this xn as decision variable in each of these items. So for sure, as you see here, if I define this fn star s is minimum of each of these fn's. For example, I am in stage 2, okay, the minimum of these elements. For sure, I can show this x n that is minimum with xn star, okay? So from the other side, sorry, the value of CSXN that obtained by setting I equal to S and J equal to XN is the cost of moving from one node to other node. As you remember, before in our slide, I told you there was a cost Cij. All the numbers that are above the arrows are showing the cost of moving from one node to other node, one city to other city. As you remember, this cost was the insurance cost that the insurance company offers us. So to conclude this item, I can say the FNSXN is the immediate cost of that stage, stage N, plus minimum future cost, okay, of the stage N plus 1 onward. So if I write it in a mathematical form, is CSXN plus FN plus 1 star XN. So this star means the stage n plus 1 that is optimum. In this case, optimum means minimum that comes and will be added to this cost. So the total of this will be the minimum, the optimum for the other stage, and so on, moving toward the first point to find the optimal solution. In the next slide, with this prototype example, I will show you the amounts and the procedure. Before starting the explanation of this slide, I should just add this item to the previous slide, that our aim is finding successively F4 star S, F3 star S, F2 star S for each of the possible states S, and then using F2 star S to solve for F1 star A. So, as you see, guys, here, as I told you, we start solving from this side to this side to find the minimum item. So, at the stage 4 of our example, as we have here n equal to 4, we should calculate all these elements for our stages. Here is easy. This F4 star S is coming from 3 and 4, that both of them, the selection is J, because they are connecting to J, 3 and 4. As you remember, the formula was CSXN plus FN1 Fn plus 1 star Xn. But as you can substitute here, if n is equal to 4, n plus 1 is equal to 5. But one important item, because we don't have anything after this node J, because California is our destination, for sure our F5 star S is equal to 0. So all what happens is this immediate cost that we have, that are 3 and 4. In our next slide, as an additional slide, I will write this explanation of formula that I told you. To complete what we learned in the previous slide, let's focus on this concept to just justify that what happens. So imagine, for example, we are in the step F4, S and X4, okay, is C, S, X4 plus F5 star X4. As you see here, guys, this C, SX4 could be one of these two items, okay? One of these two items, or this one, or this one, okay? Better saying. Let me change it. Or this one, or this one, okay? And F5 star, this is the stage 4. So F5 will be something here, but it doesn't exist. So this one is 0 in both cases. So this F4, S and X4 is or 3 from here or 4 from here, okay? The other one, S and X4. So finally, as you know, based on the formulas that we have, that for example, this F, for example, 4 star of S, in this example will be 3, this part, okay? The minimum of 3 and 4, but in the next slides, we complete all the solution. Following the previous table, when we were here at this point, okay? So now we want to move toward the stage 3, okay, when n is equal to 3. At this stage, again, we need to form this formula that we have here, okay? So we are in the stages, okay, S, stages E, F, and G, and we want to make a decision of the X3. What are the X3? Okay, the items that are coming from the stage 4 that are, stage 3, H and I, okay? So as you see here, guys, based on this formula, this cost, for example, for E and H, what is that? The immediate cost is 1, and the F star 4 that comes, which one is from the stage 4? That is 3. So 3 plus 1 is equal to 4. Let's review this 8. E and I. As you see here, the immediate cost is 4, and the item that comes, minimum future cost, that is 4, okay? 4 plus 4 is 8. This 9, again, F and H. The immediate cost is 6, and the minimum cost of future that we obtained in the previous step was 3. So 3 plus 6, 9. And the other elements can be calculated like this. But we are interested to find the optimal solution of each of these ways, okay, for each of these nodes. As we found these 3 and 4 here, we again are interested for E, F, and G. Which one is our preference? Our preference is find the less cost, okay, the minimum cost. So between H and I, between 4 and 8, which one is minimum? 4. Between 9 and 7, which one is minimum? 7. Between 6 and 7, which one is minimum? Is 6. Okay, so we have this minimum cost like this stage, in this stage, 4, 7, and 6. So we should always also write this column, okay, that is the xn star, that is the optimal solution, to know, and to know from which cell it comes. Why this one is important? Because finally, when we reach to step n equal to 1, we can follow up the optimal solutions, okay? So this 4 comes from node H, this 7 comes from node I, okay, because this 4 plus this 3, no? And this 6 comes from node H again for G, no? 3 plus 3. So let's continue the same idea for the next uh, steps and to see what is the final solution. So the time is for this n, okay, the n equal to 2. We are here, guys, okay, we want to make a decision. As you see here, from B, C, and D, all of them, they are 3 lines to E, F, and G. As you see here, again, as always, we form this formula, this n, 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 n plus 1, and n. This is the formula in this concept. Guys, this formula is only works for this problem, the stagecoach problem. Maybe this formula for the other one is different. For this reason, I told you in the very first slide, in contrast with linear programming, we can't find the same formula or solution for this work. So based on the same idea, let's follow the elements of this table. How can we obtain them? But pay attention. In each step, by using the minimum cost, we are following our objective, that is finding the minimum cost. Okay, so these elements of 4, 7, and 6, for example, for sure will guarantee the minimum of this one, and for sure these items guarantee the minimum for the A. Okay, when we find this minimum, it means this element that we'll see in the next slide is the minimum cost of this problem that we are finding. But let's see. For example, for node B, we want to know where is this 11 comes. Is the immediate cost, that is 7, and the minimum cost that comes from this stage, that is 4. 4 plus 7 is 11. The same concept happens here. 7 of the future minimum cost plus immediate cost, that is uh, that is 11, and the same happens here. 6 as a future minimum cost and immediate cost, that is 6, that is 12 here. Now, for example, let's review this line D. Okay, the line D that goes to E. The immediate cost is 4, the future minimum cost is 4. 4 plus 4, 8. I'm following this formula. D and G, okay, as you see here, guys, 6 plus 1, 11. And with the same concept, we can write this 7, 9, and 10 for node C. So as I told you, this star here is the optimal. Our optimal is finding the minimum. Between 11, 11, and 12, which one is minimum? 11. 7, 9, 10, which was his minimum? 7. 8, 8, and 11, which was his minimum? 8. So to follow up, finally, the optimal solution, we need to write to know where this one comes. So this 11 comes from or E or F. This 7 comes from E. This 8 comes from E or F. Finally, we'll see that this game doesn't have only one optimal solution. It has more than one optimal solution. So this or means this one. We'll see in our next slides what are the optimal solutions for this game. Finally, when we are here in this stage, okay, we want to find this formula that we have here. Again, like the previous part, the immediate cost plus the minimum future cost that comes from the other one. As you see here, it's n plus 1. In this case, it's 2, n plus 1. 1 plus 1 equal to 2. That is this 13, a to b 11 plus this 2. This 11 is 7 plus 4, and this 11 is 8 plus 3. Immediate cost plus minimum future cost. That the minimum between 13, 11, and 11 is 11. That this possible 11, that is minimum 11, comes from C and D. As you remember, 7 plus 4 and 8 plus 3. So these are C or D. Now in the next slide, we'll see and we'll review the different possible solutions of this example. Before going to the next slide, let's conclude what we learned from the different steps that we had. Obviously, the next slide is just explanation of here. Now we have all the tables, n equal to 4, n equal to 3, n equal to 2, and n equal to 1. Okay, so now we are ready to find the optimal root or roots. Okay, as you see here, guys, in this part says the minimum cost of the whole game is 11. How we obtain this one? Moving from 4 to 3 to 1 and this to 2, sorry, and to 1. So this 11 says the minimum cost of this game can be $11. Okay, so this 11 can only be for one option, for one route, or more than one route. Let's see how many routes do we have here. So it says that the optimal solution, because whenever we have this asterisk, I told you, we write this one to follow this optimal solution. So one possible solution is going from C, or the other possible solution is going from D. So it's AC or AD. At this moment, we have two optimal solutions. Now, to find the rest of the way, we should go to this table. Okay, C. C is the next step is E, and D here has two next steps, E or F. So now, as you saw, we have three optimal routes up to this point. They are ACE, ADE, or ADF. Okay, based on what we have here, I repeat, A, C, or AD, and this AC is ACE, this AD is ADE or ADF. Okay, so E or F, the total of this part. E is going to H and F is going to I, this part. So I have A, C, E, H up to here. A, D, E, H, A, D, F, I up to here. These are three roots up to this part. And finally, obviously, this H and I, both of them, will finish in J. So our optimal solutions with all of them with the same cost is 11. What are them? ACEHJ, ADEHJ, ADFIJ is the third one. In the next slide, you have all these roots in a written form. In this slide, we have the same explanations of the previous part. We start with n1, okay, n equal to 1, as you see, as I explained before, C or D. In case of selecting C, we should follow with E. In case of selecting D, we should follow in two different lines, E or F. As you see here, this solution, and this solution are the optimal solutions with the cost of $11. And all of them obviously will start from A and will end in J. J, 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 from Missouri to California. And here, if we show these roots, you can see them. 4 plus 3, 7, plus 8, plus 1, 8, plus 3, 11. This one, 3, 4, 7, 1, 8, plus 3, 11. This line, 3 plus 1, 4, 4 plus 3, 7, plus 4, 11. As you see here, the explanation we have here is exactly like the previous part. All these three roots will give us the minimum cost that is 11. It means that there is no more roots with the cost less than 11. So the minimum cost of the all possible roots will be 11. So based on this stagecoach problem that we reviewed as a prototype example, we can list the characteristics of dynamic programming problems in some categories, okay? That problem, as we learn, can be divided into stages with a policy decision required at each stage, okay? As you remember, for example, in this stagecoach problem that was minimizing the cost, we focused in each step, and by finding the optimal solution that was the minimum, we just move backward to find all the steps, and then we found the correct solution. And each stage has a number of states associated with the beginning of the stage. Obviously, all the nodes that were related to that stage. The other characteristics that we see here, the policy decision at each stage transforms the current state into a state associated with the beginning of the next stage. Solution procedure designed to find an optimal policy for the overall problem. Obviously, as we saw, it was the goal of this one. And given the current state, an optimal policy for the remaining stages is independent of the policy decision of previous stages. Okay, so based on following the goal and objective of our example, we do that. Again, as we saw, its a solution begins with the last stage. As I told you, is a recursive relationship. It's a backward movement, can be defined that identifies the optimal policy for stage n, given the optimal policy for stage n plus 1 by the immediate, okay, by the immediate cost and the future cost, that is n plus 1, we find this uh, optimal solution. As you see here, this optimal solution could be minimum or maximum. In our case of stagecoach problem, we were searching the minimum cost. It was the formula of that. But I repeat, always the formula is not like this. Based on the example and understanding it, we should make this one, and based on this relationship of n and n plus 1, try find the optimal solution that is minimum or maximum. And finally, using the recursive relationship, the solution procedure starts at the end of the works backward. And always, guys, this table is valid for all the dynamic programming problems. The Sn, the remaining, the Xn is the decision between these items. This formula of Fn, Sn, and Xn that I told you based on the dynamic programming problem will change, and this optimal solution that could be minimum or maximum, and this X star n that shows this one from what point comes. In the next slide, we start the concept of deterministic dynamic programming problems.